So why is supply chain design so important? Well, basically it's because we have so many choices. We've talked about this in SC1X, and we went over many different ways to forecast product demand. There's not one way to forecast demand. There are many different ways that depend on the situation at hand. Same thing with how much inventory to position and where. Same thing with how to move product between facilities. Do I use fast transportation? Do I use slow? These are all a function of the situation. We also talked about different ways of segmenting customers and how you can collaborate with customers, how to work with suppliers, even the whole idea of how you organize your supply chain function itself. Is it decentralized? Is it centralized? So all of these things, you have these different choices, and to include selecting locations, which we'll spend a lot of time on in this next lesson. So we have all these different choices, but we also know there's no single best way for all situations. It's not like there's this one holy grail supply chain that everyone should and will eventually get to. They all differ based on the situation of the market, the customers you're serving, the product characteristics, all of these things. And it's not just different between firms. It's different within a firm, because a single firm will typically sell to multiple different types of customers, and they'll segment them accordingly. And they might have very different types of products, and they'll segment those accordingly. So I want to take this opportunity to do a really quick review of some of the options and the choices that we talked about in SC1X that you're going to be using for supply chain design. And I'm going to focus in on forecasting, inventory, and transportation. So this is a very, very quick review of SC1X, and so feel free to skip this if you're very familiar with these concepts. So let's start with demand forecasting. The thing that determines the type of forecasting method to use really is all about history. Do I have it? Do I have history in terms of the market where I'm trying to sell to, as well as the product that I'm trying to sell? If you have both of those, if you have history and you think it's going to repeat itself, that's all about time series and exponential smoothing. I'm going to say that what happened in the past is probably going to happen going forward. And so I identify and recognize the underlying patterns of level, trend, seasonality, and I use that to project my demand going forward. There are many, many products. Most industrial products fall in this quadrant because there's a lot of history out there. What if you have no history though? So you know the market, but you don't, it's a new product to that market. Well, this is where you use a looks like type approach, where you look at similar products that you've launched in the past and see, okay, they did such and such, so therefore I think this product is very similar to this product, so you use that approach and you think their demand is going to be similar. Same things if you have new market, but you know the product, so this is something new to market, but you already know the existing technology, and here you're going to get experience or experimental input, and it's kind of more qualitative input than quantitative because you don't have as much history of the market, so you get expert opinions. And then finally, if you're down here where you have no history of the product, no history of the market, you're kind of off in the deep blue waters. This is where you use forecasting approaches to really help understand, to get you a better sense of the whole market. And this is where we talk about Bass diffusion models, scenario planning, Delphi approaches, or expert panels. Again, it's somewhat more qualitative, but you're going to try to find something to help guide you. Now, regardless of the type of forecasting method you use, the approach, there are three things that are always going to be constant. One, forecasts are always wrong, but don't stop there. Do something about it. You want to use ranges, and you want to track your forecast error. I'm always shocked at the number of companies that do not track their forecast error, either accuracy or bias. It's amazing. Always track that. We know that aggregated forecasts are more accurate. This is why we use risk pooling to reduce the coefficient of variation. And shorter time horizon forecasts are more accurate. This is why postponement can often make sense, because we're making that last forecast very close to when the product is going to be used. We postpone the customization. So regardless of the method of forecasting, we're always going to look at that error term, which is the actual demand minus the forecasted. And there's three metrics that you should always keep in mind. One is the mean deviation. This is a great metric to show bias. So this will help me determine if I'm over forecasting or under forecasting over time. Then you've got MAPE. MAPE is widely used to help compare different forecasting systems, and it's simply the absolute value of the error divided by the actual amount, and you take an average of that. So it puts things into perspective as a percentage. For use in inventory models, we use the root mean squared error, the RMSE, which is simply the sum of the squares of those errors, and then you take the average of that and take the square root. So we use this when we start figuring out our safety stock. So all three of these metrics are valid and they have a separate purpose, so you should really always track those. Then we went into inventory management, and just as history of demand is the primary driver of the approach for forecasting, the primary driver for inventory management is your demand variability and your horizon, your planning horizon. So if I have something that has no or very little planning horizon, very little demand variability, but a long planning horizon, then I'm probably going to use something like an economic order quantity, EOQ. And so this is where we're trading off fixed costs and variable costs. And so the demand variability is next to nothing. And you have a lot of items that fall in this, especially in industrial settings. So I'm going to order Q star every T star time periods, and I'm going to order Q star when the inventory position, that's the inventory on hand plus what's on order, is equal to my expected demand over lead time. Now you have an opposite situation where I have a very short horizon, it's one single period, and this could be selling Christmas trees, sushi, ice cream cones, newspapers, things that I can only sell during that one period. No one wants to buy yesterday's newspaper. So I have a single period and my variability can be quite high, my variability of demand. And in this case, we showed how to make a trade-off again, but this time between shortage costs and excess costs. Well, the excess cost is obvious, right? If I'm selling Christmas trees, the price I can charge for selling Christmas trees the day after Christmas is pretty low, right? I'm not going to make much money. In fact, it might be zero. But the shortage cost is another side that we don't always think about. If I run out of selling, for example, Christmas trees a week ahead of time, that's a week of sales that I missed. So you've got shortage costs and excess costs. And what this model does, the news vendor or newsboy or single period model does, is it makes a trade-off between having too much and having too little. And we found that ordering the amount, the Q star, at the start of the period to cover the amount of the demand distribution, the probability that my demand will be less than what I ordered, is equal to what we call the critical ratio. And we showed how to develop this critical ratio as a ratio of the shortage costs over the sum of the shortage and excess costs. So the real differentiator here is that for EOQ, we assume very, very low demand variability, but a long time frame. And for the news vendor problem, or the model, we assume a very short time period and very high variability. But there's a lot of cases, obviously, in the middle, and they kind of combine both approaches. And we have two main classes where we can set up inventory systems for each of these. And so for the replenishment period, where I'm trying to, again, determine how much to replenish and when, I've got two major classes, continuous review and periodic review. So for the continuous review, we've talked about the SQ system, which is order point order quantity, SQ. And the policy is I order Q, the amount Q, if the inventory position is less than this trigger point, little s. Okay, how much is Q? My old friend, the economic order quantity, right? This is Q star, the EOQ that we just talked about when we assumed that demand variability was relatively stable. It's a good place to start. Now, how do I set this S? What I'm saying here is my demand, or my inventory position, I track that, and if it crosses this threshold, I'm going to order Q. I'm going to order that amount up, and then inventory goes, it shows up, and the same thing happens when I cross that threshold, I place an order. So I place an order while I'm continuously monitoring the inventory position. So how do I set S? Well, it's going to be the expected demand over lead time, right? Because if I place the order here, it's not going to show up until L time periods later. So I want to have the average, plus I want to throw in safety stock. This is safety stock. It's going to be some safety factor K that we can take off of whatever the distribution looks like, multiplied by the standard deviation of the forecast error over that lead time. So That's a continuous review policy, pretty widely used, but even more widely used is a periodic review. This is where I will only review my inventory every R time periods. That could be once a week, every 2 weeks, once a month, every third day, whatever. I have this review period every R days, and I'm going to look at that time period, look at my inventory position, and I'm going to order up to this big S. That's why it's called an order up to level. Sometimes it's called a par level. So I order up to, so I'd order this amount. For here, I'd order this amount, and it's whenever my review period comes up. So how much do I order? How do I set this S, this order up to? Well, it's going to be equal to my expected demand over my review time plus the lead time, because that's the next time I'll actually get the stuff in. Plus my safety stock, again, my safety factor, and then the sigma over the same time period, the replenishment and the lead time, and that's my variance of my forecast error. So 2 different methods, continuous review, periodic review, and they're very similar. So then we went into transportation. Transportation gives you many different options to get product from A to B. So 3 basic approaches. One is the direct or one-to-one, point-to-point moves. If I have sufficient volume in a move, full truckload, full container, then it might be worthwhile for me to move it directly from one point to the other point. As the shipment size decreases, though, it might not be economically justifiable to ship something direct. I might have to do a one-to-many or a multi-stop. So instead of a full truckload, let's say going for here, maybe each one of these has a quarter of a truckload. And now it would make it economically justifiable to do a multi-stop. As my shipment size gets even smaller, I can need this many-to-many, where I want to combine as many things going to each one of these customer locations. And so that requires a mixing center, cross-docking, or a hub operation. So you have all these different ways to distribute product from a distribution center, in this case, to a customer. At the end of the day, we showed that you have these options. This is the strategic network. So moving product from A to B, for each of the options, I can summarize them in terms of how much it costs, how long it takes L in terms of lead time, and then the variability of that lead time, sigma. So I have all of these. How do I combine those all together? Well, this is where the total cost equation comes in, because I look for the solution that minimizes my total cost if I'm looking at designing a cost-based system. So my total cost is my purchase cost for each item, plus my ordering cost, plus my inventory holding costs, which consists of 3 components. My cycle stock, the inventory I expect to use during my typical replenishment cycle. My safety stock, kind of my buffer in case demand peaks or something happens. And the amount of inventory in my pipeline, the stuff that's in the boat, in the truck as it's being delivered. And then I've got this final term, which is a cost. It's kind of a holding for the stockout cost. If I'm out for each individual item, or if I'm short for the event, there are different ways you can cost this out, but it's all of the stockout types. So what we can see, hopefully, is that the forecasting and transportation impact my total cost. As my forecasting error gets worse, what happens? Well, my sigma DL gets bigger, right? So that means my safety stock goes up. If my transportation gets slower, then what does it do? It increases my pipeline inventory. It also increases the length of time that I have to hold inventory, so my safety stock goes up. And it can also impact my costs for each order as well as for each item. So forecasting and transportation all impact things, and it really comes down to setting that safety stock. In a lot of cases, the inventory is the prime driver. That's where a lot of the money is. And so we talked about how we can set these based on service metrics. So we set the K value based on a level of service we want to hit. 95% of the time we don't have a stockout event, or my item fill rate is at least 99%. Or we can find a K that minimizes the total cost if I put a dollar value on each stockout event. The last thing we did is just to combine the variability of lead time with the variability of demand. And I just have the equations here just for reference. But what we did in SC1X then is we went through each of the primary functions, forecasting, inventory, and transportation, and showed different options and when to use what. And what we're going to do for the rest of this course is apply those in different ways and figure out when to use which type of approach.